So you probably want to know more about reliability, whatever it means literally. I also mean the same thing. If you want to have a measure of how reliable the software is, a measure means a quantitative measure, that is software reliability. So briefly speaking, you have to come up with an index or a measure or some kind of metric which will tell you how reliable the software is. Now, whenever we see that, how reliable a software is, we have to have pretty good idea about what we mean by the software being reliable, right? So, before getting into this, it may be a good idea to, to tell you that, especially to those of you who think that software means the kind of things we work in the lab and produce a lot of results and things like that. I mean, it is so invasive in our day-to-day life. That we cannot probably think about anything without any use of software. It includes almost everything we do in our day-to-day life, including this one also. The way I prepared it for last couple of days, that also needed some software. So, and while doing all these things, you must have faced problems now and then, that this is not working. There is linking problem. There is some output is not to your satisfaction, and all this kind of dissatisfaction with the software you may have faced at least once or twice in your life, maybe more. So the word reliability derives strength from that particular aspect of your reaction to the software, that whether you are satisfied with the software, whether there is something you are not satisfied with, so that would be unreliability, and reliability will be something that some service the software has given and you are satisfied with. So whenever we talk about software reliability, we can first think about the failure, what we mean by a software has failed, and then we can think about not having that failure. So that would be my satisfaction. So I am basically a whole array of things can happen when you use a software or when you use a device which runs on a software, and I am basically trying to dichotomize that into two things, that you are satisfied with it, you are not satisfied with it. So if you are not satisfied with it, then I can say that it is a failure if it doesn't produce the intended result or the output within during its operation. And we know this can happen in many different ways for many different reasons. And I would just like to list, maybe many of you know that, some famous software failures. The famous Y2K bug, and there was a lot of business to fix this bug in the late 90s, because you know that the year was written in 2 digits term, and when we were near the century, then the realization came that we have to fix it, because the calendar will go berserk because of this problem. So then that's the problem of fixing that came up. So this kind of dissatisfaction with the service was there because there was not that foresight that in near future I have to have my software well built so that it can withstand the kind of trouble which was going to come. Mars Climate Orbiter, that was in 1998 by NASA, and there was some software problems, coding problems in the guidance and software. So that was not as famous as the Y2K bug. Radiation overdose by some Therac 25 machines. There is some kind of radiation to cancer patients, and there were some overdose because of some problems with specification of units. And in this regard, I remember also in the 80s somewhere in Canada, I was a student in Waterloo at that time. There was an air crash, and apparently at that time Canada was going through the change to a metric system from the British system. So they had everything written up in gallons of liters, and there was not enough fueling to that aircraft because of that kind of change. So that was something, and these are very obvious things once you see it happens, but when you go through it, it becomes sometimes difficult to see what kind of problems are lying ahead and lying around you, and how many problems you need to fix. Power blackouts in US, this was pretty famous in the early 2000s, and there was some problems in the grid software, it seems. And very recently, last year, we had this Quantum-Kai ransomware attack that all of you probably remember this. And these are kind of, here probably the software was not, the fault tolerance was not good enough. Like it could not foresee the kind of loopholes the software has through which some hackers could get in, and that kind of problems. So anyway, these are major software failures. I just told you because I wanted to make it in a storytelling fashion. But otherwise, in your day-to-day life, you certainly see major problems, minor problems, and some of which you probably report to the software manufacturer or software developer, and some of you don't probably report. You just ignore it and try someone else, wait for someone else to come and fix it, and things like that. But anyway, these are just statement of problems, and how you handle, how you define this reliability, and how you come up with certain things which should be acceptable to others. That is the problem, and that is the lecture we want to give. So you want to have a measure of how reliable the software is. Several definitions exist. In fact, depending on the problem at hand, you probably can guess it. I told you that reliability, concept of reliability comes from what you get your satisfaction from. Now, if you are happy with some moderate level of service, then your concept of reliability may be different from if I am happy with very low level of service. So see, it depends on the person working on it too. So you have to have pretty good specification of what you are satisfied with, what you will call failure, what you will call a success. So that's where the reliability definition comes to. But anyway, in all those definitions, a commonality is that that the measure should be, it should be proportional to the probability of failure-free operations or error-free operations, and over a certain period of time, over a certain uses. Like if you let it run for long hours, and if you want your software to serve you for next 10, 20 years, that is probably a little too much. So you have to fix your time also. I'm grateful to previous speaker Sourangshu that he emphasized the time concept in somewhat indirectly, but he brought in this topic. So that comes in the reliability definition as well, that you have to say how long you want to be happy with that software. And that is the kind of dichotomy you have to bring in. Okay, so this is a very general definition. You will see, I'll try to give you examples, time permitting, and we'll see that definition of reliability. I also mentioned that it depends on the context. It depends on what you are happy with and all this. But reliability of software in general can be defined as probability that the software will serve its intended purpose. See, the intended purpose. Now, what is that intended purpose? You have to specify before you get to the definition. And it serves for a specified period of time. I'm talking about specified period of time. Sometimes you may be able to write it in a specific number of times. Like if you are going to ATM machine and you want to see how many operations in your ATM visits, how many times you want to see that the machine is working with you. And it's not just you, how many customers are satisfactorily being served. So instead of period of time in a continuum, you can think of it as a discrete scale, number of times. So it depends on what you want. And Also under a very specific condition that, the environmental condition, that other like other related conditions could be there. So the specific condition also sometimes needs to be spelled out. Okay, so in this talk specially, I would like to say that the major objectives of, rather broad objectives of the software reliability problem would be to identify the relevant data and select or develop some modeling approach. Because you are going to talk about reliability, something you should be able to calculate based on some data. You have to have, you just can't have a machine and say that this is 99% reliable or anything like that. You have to have some test data based on which you would be able to say. And when you say that based on some data, it means it's an estimate essentially. So before you try to estimate the reliability, you have to identify the kind of data you are dealing with. And based on that kind of data, the nature of data, you will be developing or selecting some existing model. And then once you have the model, you define reliability in a very specific manner, what you want. And we'll get to these exercises one by one. And you have to somehow figure out a way of computing or evaluating that reliability under whatever chosen model you select. And in that model, there will be some unknown parameters. You want to estimate those parameters. And then since you can compute the reliability in terms of those model parameters, you should be able to plug in those model parameter estimates to get the estimate of the reliability. That's essentially the broad objectives of reliability. So let me tell you how the data usually comes. Once a software is developed, by that there is a developing team also, and they might work in batches, in groups, and but once it is there, then the software verification step, it usually goes through two major steps. One is called static variation, where essentially the routine job of code verification and see the design of the software, like whether it is compatible with your client's requirements and things like that, and those are looked into, and complexity and whether the algorithm you are looking into is followed properly or not. All these fine details are looked into when you go through static verification. But when you are getting into dynamic verification, that ensures the actual execution of the program of the software during its runtime. So that is the dynamic verification. Sometimes it is also known as software testing. That is the more popular name, software testing, a process of executing the software problem. And in fact, the goal is to find problems, find errors, and see how we are getting the error, and through application of test cases. When you develop the model for discovery or detection of errors or faults, when you observe that, or as you observe that, the modeling approach depends very much on how you are observing those errors, how the errors are turning up, how you expect these things. So that's how you would be trying the modeling approach when you see that, when you notice that pattern, that how the error detection is taking place. Okay, before that, let me just outline different methods of different ways of software testing. So once the software goes through static verification, then there's something called, what used to be the practice called black box testing. The tester had no access to the source code. The tester does not have to be knowledgeable about the about the content of the software. What the software is doing, what is it all about. He is given a black box, and the inputs are fed in and the results are coming out. If there is a problem, he would approach the management that there is a fault coming up. So it's more like unskilled labor here. So the tester doesn't know what is there inside. He's just operating the machine. So that's how the test bed, testing used to go on at the beginning. Yes?
Is it supervised testing or unsupervised testing?
It depends on what you mean by supervised and unsupervised testing. I probably don't know those terminologies, but if supervised means that if somebody is watching over them, I suppose the management is always watching over them, whether they're, working or not. So, is there anything else you mean by supervised testing?
Yeah, I'm talking about when you are taking the output, if you have the already desired output, you are comparing the output with the desired output, or you are just comparing with the input to output. What's the comparison?
No, that is supplied to the tester, that the input is supplied, so and he's given the intended output also.
You write output with the desired output.
That's right. So he just matches whatever is, he knows what is expected, and if it doesn't come up, and if there is a problem otherwise also, he just reports to the management. So that's black box testing. But I mean, that's very primitive. I don't think this goes on now. This white box testing is rather known, where the tester has full access to the source code and the content and everything is known to them, and they certainly do a better job in terms of testing and also reporting the errors and things like that. Gray box is somewhere in between, possibly no access to the source code, but they know what is this software is all about. With the invent of all those, internet facilities and social media and lot of, interaction between, the users and the developers, software developers. This has become a new source of software testing data, user-driven testing. So when the software is already in the market, the customers, while using, if they see some error, I mean, we might have seen it, suddenly some error box opens up, and most often we would simply ignore it, cancel it, or you are requested to, report it to the developer. So I think most of us, like me, who are casual users of the software, will click the cancel button, right, and get on with my own work, right? So, but those who really understand, the skilled persons, they would probably report it because they know it has its use. So the developers will collect those feedbacks, and they know that there are the problems which are being reported, and those kind of data called user-driven testing, and it has become a big challenge now, where the users voluntarily report through internet. And these are called bug database, where those reports are being collected and suitably analyzed afterwards. The analysis of this kind of database is a big challenge because see, previously, how many testing you did, how you executed, and how many errors came up. So it's kind of, if you have to look at proportion of errors, you have a numerator, you have a denominator. It was pretty easy. You just need some sophisticated modeling. But here the denominator is rather unknown. You don't know how many people are using, for how long. You have absolutely no information. You suddenly, from time to time, you see some reported defects. And so the denominator is completely missing. So to get to any data or any idea about what proportion of defects there is, or what is the rate of defect there is, it's very difficult to say. And the users are of all kinds of varieties. There are some skilled users who would probably more serious, and they would click the right button to send to the developers. And there are casual users like us who would click the cancel button. And there are skilled people who would know that this is important, serious, so it should be reported. And there are very casual users like us who would not know the seriousness of that fault, who will simply click the cancel button and go on with our own business, right? So the developer has to deal with all these different kind of people and somehow try to form a denominator so that something can be said about the rate of defects or the proportion of defects and things like that. So I will give an example on that, and probably another example on the white box testing, one after another. So now few aspects. Once an error occurs leading to detection of a fault, it is understood that it has to be debugged, right? That's understood. So there are two aspects in that. One is immediate debugging. So as soon as you detect that, you debug it immediately. Most of the models considered previously, they considered immediate debugging. The testing also pretty much followed the same rule. But there is some new concept came up called periodic debugging, where the detected errors are recorded but not debugged immediately. There is a debugging team who comes probably periodically, and when they come, then all the detected errors by that time, or since the previous debugging time, they will be all debugged, right? Now this is an easy concept, but debugging is not as easy as it can be said. I mean, all of you are faced with some kind of programming exercise. You know, debugging is probably the toughest thing in software development. So perfect debugging and imperfect debugging, these are also two issues. And most of the models we assume that perfect debugging, because otherwise it's very difficult. There is absolutely no direct data on whether a debugging is perfect or imperfect. So to tag a parameter to a certain debugging exercise to be called perfect or imperfect with certain probabilities or things like that would be absolutely impossible to, I shouldn't say impossible, difficult to get an idea of. Unless, of course, there is a more sophisticated testing where a further validation testing takes place whether debugging is perfect or imperfect, so that you get certain idea about the proportion of imperfect debugging and things like that. Okay, so these are just certain issues which are built into it. So as we go on describing our examples, we will not get into that, but I discuss some existing software reliability models, and it is the idea is, as I said, that it will be to provide some probabilistic model for the defect discovery process. That's what I say, the process of how the defects are discovered or detected. So usually it is done on continuous time scale, as you have seen, but I also mentioned that it can be in the discrete time scale. That is probably more realistic, because every time you do a use, you run the program. So one run is equal to 1 unit of time. You could look at it that way. But modeling usually depends on the kind of data that is to be expected. Like for user-driven testing data, the modeling has to be different, because I said the inherent problem of not knowing the amount of uses, not knowing the denominator, is a big challenge. So there are some limitations also which one has to be looked into. Okay, so the earliest modeling approach was through something called non-homogeneous Poisson process. Shrangshu had mentioned among marked point process, that is a more sophisticated stochastic process, that is probably one of the simplest one, where it is assumed that the errors over time, as you go on testing and measure the time in continuum scale, that the errors take place according to, if you look at the time points of errors occurring or being discovered, they follow what is called a non-homogeneous Poisson process, NHPP, and by any time t, the total number of, or the cumulative number of errors, if you denote this by capital N T, that is a random variable, and a Poisson random variable with mean that big lambda t. And big lambda t is an integrated function where small lambda is called the defect detection rate or defect detection intensity. Without getting into the details about what NHPP is all about, the defect count NT has a Poisson distribution, and for any interval I, it can be union of intervals also. So you just look at some subset of the real line and count the number of defects you have in that subset or in that interval. And I will be Poisson distribution with mean integrated over that subset of the integration of that intensity function. Not only that, if you have two disjoint time intervals, the counts in the two time intervals will be independent. These facts can be exploited to estimate the related parameters in big lambda t. Big lambda t, there will be some related parameters, unknown constants, which need to be estimated. And this intensity function usually modeled as a parametric function, as I said, and those parameters to be estimated. These are the there are many other models, but these are the three models. In fact, they are derived from some differential equation on big lambda t, that how big lambda t changes over time. So they have some hypothesis over that. Like in the first one, big lambda t is assumed to change linearly over time, and so on. And in the second one, I think it is exponentially. And from there, algebraically, you can derive the expression for small lambda t and so on. So there are many other models, but you see these are all in the 80s, and this is pretty pretty much the first approach which people took. And one might be a little worried about this kind of modeling also, like this defect detection rate lambda t. If you look at it, it's a function, it's a deterministic function, and it does not depend on your previous history. How many defects has been detected, or how much time has been lapsed. It doesn't depend on, okay, it depends on the time, sorry. How many attempts you have made, all other, there are previous experience. It would be very prudent to model the intensity rate lambda t as a function of your previous experience, how many has been defected and all these things. And this kind of modeling doesn't take that into account. So this has a lot of limitations, and so it happens afterwards. They change this a little bit, and this intensity rate would depend on number of errors discovered so far, number of attempts you made so far, and all these things. It doesn't remain NHPP anymore. It becomes something like marked point process, and the theory is little more difficult. Not impossible, but a little more difficult, but they can be done. And there have been approaches like that in the 90s. Interfailure time model, so you look at the failure times and the time between failure times. So some people modeled it that way also. And if T1, T2, Tn are the interfailure times, and n is the number of defects you have discovered, then what you do is look at the joint distribution of n and T1, T2, Tn, try to model that. When I say joint distribution, it means you try to model what is the probability of observing small n, detecting small n number of defects by certain observation time. And those are the time points when you observe, or the interfailure times. And the model parameters would be estimated by method of maximum likelihood, and this can be done. So these are some examples. Again, you see that these are in the 70s and 85s. There are some Bayesian approach, and this has been, I remember the organizer Sudipto is one of my collaborators in some of our recent work. He knows that, where is Sudipto? He's not, oh, there. He knows how difficult it is to publish papers if we write that it is Zielinski-Moranda type models. Even if we say Zielinski-Moranda type, the people don't like it anymore. So it is way past there now. Okay, so I would get into examples. I don't know how much time I have. 10 minutes, okay. I would probably require 2-3 more minutes to cover both the examples. Let's see. So this is a software for a flight control system. We got this problem from ISRO. When the satellite gets launched, then its flight path is controlled by several units of softwares. So this is a unit of software we looked into, which is for a flight path of about 20 seconds. I remember for 20 seconds, this is a huge software, and they gave us. They had a lot of testing data, and they wanted us to look into that. And after all this static verification and all these things, they carried out some testing, and they had done it in 4 versions or 4 activities they called. This is the first time I'm talking about modules, but all of us know that software has different modules and all these things. Previous modeling approaches did not take care of this modular structure, and this first version had about 187 integrated simulation runs and so on. After each version, after each activity, they go back to static verification again and some modular level testing and all these things. So they have a lot of intermediate things between 2 versions. And then during this activity, during this version, there's 227 runs in the second version, for example. They carry out these simulation runs one after another. They are complete, simulation runs of that unit of software. Okay, so errors detected within an activity or within a version, they are corrected at the end of the activity. So they are recorded, but corrected at the end of the activity. It means it is like periodic debugging. Remember, they are not corrected immediately. And for each module, we observe the number of simulation runs that is already there. So for 126 modules, each of them has gone through that, except 2. And we also observe number of failures in different activities. Unfortunately, when they gave the data, they did not give us the time of failure, the identity of the run when the error took place. So the 6 failures, as far as I remember, version 1 had 2, version 2 had 1, version 3 had 3, version 4 had 0, something like that. But I don't remember exactly, but there were about 6 errors in all these. So out of so many runs, only 6 errors, I'm sure you would call it very reliable, and that's a commonsensical definition, but one has to develop a convincing model and things like that. So in this context, the definition of reliability, I wrote it down, you can read it up quickly. The thing is, the reliability is that if another single run of the integrated simulation testing is to be carried out at this time with a randomly selected input from the set of all possible inputs under the identical computing environment, their test run was under simulation runs. So they have a computing environment and other conditions. Then the probability that the software probability of no failure due to this particular unit, that would be defined as the reliability. But I'm talking about no failure in the one more simulation run. And that will be taken as, equated with the probability of no failure in actual run, in the actual mission when it takes place. Because they cannot afford so many runs, actual missions. They cannot afford that. Okay, let us look at some features. The time domain is inherently discrete. They have one after another run. And each run has one discrete time. Debugging is not immediate, periodic debugging. There is a modular structure which needs to be incorporated. Identity of the module is not there. Module-specific covariates are available. Complexity, history of errors during the static variation stage, and also modular level testing. All these, there are errors reported during that time also. All this history has to be incorporated in the model. And different modules have different extent of exposure, different kind of testing, and identity of the failure is also not available. But identity of the module is available. So you see, there are so many runs. Out of those many runs, so many failures. Those of you who are familiar with binomial distribution, you can probably immediately see any elementary statistics course will have this binomial distribution. It's very apparent. So we fix a binomial distribution, but we model the probability of success or probability of failure, the P, as a function of the number of runs it passed through, the history, and all these things, the complexity of the module and everything. So it's a very complicated modeling, and I'm not getting into that. And this probability can be modeled incorporating all those covariates, and there is procedures called generalized linear models, or some of you probably know about logistic regression model. So there are packages available for logistic regression model. You can straight away use those packages, provided those packages are reliable, but there are reliable packages. And so the analysis becomes easy once you, although the modeling becomes a lot more complicated, but analysis becomes easy in the sense that that you can use, you don't have to write your own program to do the analysis. So only in that sense. Okay, what is the reliability? In the 4 activities are over, that would be computed as the product of, the product is over 126 modules. The conditional probability that that there is an error-free run given the experience up to the end of those testing. So given all the experience up to this testing, and we assume the models to act independently, that is a strong assumption again, but we had no other way of knowing otherwise. So this reliability will involve all those model parameters, how they are dependent on the history and probability of success and all these things. And these model parameters can be estimated using those packages, along with their standard errors and all these. Now, this is, first one was one measure of reliability, that probability of no failure. There is another version which I did not talk about earlier, but there is this MTTF is probably familiar to some of you, mean time to failure. The larger it is, the better it is, that at least I can get a failure-free operation for so long period. So mean time to failure. Similar to that concept, we look at expected number of simulation runs needed to have the next error-producing run given the current testing experience. So after all these testing through 4 versions or 4 activities, sitting today, how many more runs I can get, how many more error-free runs I can get on an average or in expectation, right? That is another measure of reliability. So some people look at that also. So we looked at both the aspects, the probability of no failure in the next run or number of error-free runs from now on. So these are the 2 things we looked at. Sorry, what did I do? So the estimated reliability is 0.9979. It means if you have, 21 out of 10,000 runs might give errors. That's the kind of reliability that software had. We had a standard error also. Sorry. And the confidence interval 0.9929. The mean time to failure estimate was 476. So I can get next 476 error-free runs on an average. And those confidence interval statements are also there. Now, I probably don't have to say much about confidence interval. These days, even the newspaper articles give plus minus something. So all of you know that. So this is pretty, considered to be pretty good reliability. This same data Sudipta and I, we also analyzed using more sophisticated modeling approach 2-3 years back, and we got pretty much the same reliability. So Sudipta, could we improve on this? Maybe 9986 we did, right? Where is he? I don't know. But anyway, but I mean, I won't call it an improvement. I mean, from 0.9979, if you get 9986, we are not sure that we are improving on it, because the actual reliability we don't know. We are only estimating it. Just because it is higher, it doesn't mean it is a better estimate. Okay, so I will go through this very quickly, the modern bug database. This is a specialized software where the software users can report defects, and the reported defects are reviewed and determine whether they are really 2 minutes. Good. They're really defects or not. And every confirmed they have this. And this is a Python database where it is there. And the challenges, I got into the challenges, I talked about it already. Contains user-reported software defects subject to uncontrolled and unavailable uses of software. Usage rate is a function of time, and that function is unknown. Reporting depends on the user, specialist or casual. Distribution of defect type depends on unknown use cases of the software. No existing model for software reliability considers these important confounding factors. I say confounding means that which basically confuses different aspects of the data. And due to uncertain usage pattern, modeling based on time scale is inappropriate, because we don't know how much usage is going on. So time scale is totally inappropriate. We have to come up with reliability measures which is independent of time. And this is something we try. This uses the this modeling approach uses the classification of reported defects into multiple types. And maybe one is of primary interest, and we want to find out that error-free with respect to that if that particular defect type occurs, we'll call it a failure. So we're basically dichotomizing the thing again. And the model is, our model is non-parametric with respect to that uncertain usage rate. When I say non-parametric, it means no modeling assumption is made regarding that usage pattern, because that is unknown. I cannot estimate that model, even if I try to model it. So that results in some new concepts in the likelihood theory called partial likelihood analysis. So we use that. And the reliability metrics we come up with, that also do not depend on the usage rate. The partial likelihood essentially looks at probability that the currently reported defect is of the recorded type, whatever you have recorded, given the types and times of the previously reported cases and the time of currently reported case. So this does not depend on the usage pattern. And look at this, the previous history is also incorporated in the model, in the likelihood. The only thing we do not incorporate is the usage pattern, because we don't have it, right? So model parameters can be estimated again by GLM procedures. So this is the Python bug database. This came in 2 versions. So there are 3 types of defects: crash, security, and others. And this is the total count. So, and maybe no point spending more time. Let us look at reliability metrics. We only 2 types, we consider 2 types of defects, say crash and others. So crash being the primary type. So I want to make sure, so mean number of defects to failure, like MTTF, I call it MNDF, the expected number of defects other than the crash type, that will be reported before a crash type is reported. So crash type is the failure. So before the failure occurs, how many more defects will be reported? That is my MNDF. That is similar to MTTF. And similar to reliability, a probability of not having a crash type defect in the next capital N reported cases. So that also, sounds similar to probability of no failure. These 2 metrics do not depend on the usage rate. That is I am harping on, that does not depend on the usage pattern. this can be used for 3 types and other analysis also, multiple type can be generalized. I just, so that it can be seen easily, understood easily, I looked at into 2 types. So this is my result with the 3 type analysis. Let's look at 2 type analysis. So crash is my primary interest. So reliability that there will be no crash type failure out of capital N equal to 10 such defects is 0.44 in both the versions, 0.44 and 0.47. So if you look at this, it appears that Python 2.6 was better. They probably did not need to launch the newer version 2.7. But you know, if you look at the standard error and make confidence interval type statement, they are statistically same. These 2 reliability statements. And MNDF is 11, so maybe it means about 1 in every 12 would probably will be a crash type defect. And with the 3 type things, the 3 type modeling, the crash results are very similar, but the security results seem to be more reliable. So the security type defects are getting rarer and rarer. That would be, with respect to that kind of defect, it is, the Python seems to be more reliable. But the point is, we could compare the 2 versions, Python 2.6 and Python 2.7, to see that their reliabilities are pretty much the same, and probably there was no need for introducing this Python 2.7 version. It didn't make any real impact or real improvement in that. Okay, I'm sorry if I did not tell you the complete story of this interesting data analysis and this database and all these things. This is rather recent. A couple of years back we did this analysis, but the ISRO data